Zero-knowledge proofs let you prove something is true without exposing the secret behind it. That idea powers privacy-preserving credentials, verifying age, membership, or graduation status while revealing only what the verifier actually needs to know. We've already built the foundation: identity models, verifiable credentials, DIDs, and the cryptography behind signatures and verification. Now we'll use that foundation to understand zero-knowledge proofs and how they enable selective disclosure in privacy-preserving credential systems. Traditional identity checks often reveal more than necessary. To prove eligibility, you might hand over a full credential with your name, address, birth date, license number, and other details. Zero-knowledge proofs change that pattern. The verifier gets confidence in a specific claim, such as over 18 or valid license, without receiving the underlying data. That protects users, reduces stored sensitive information, and lowers compliance risk for organizations. At the core, a zero-knowledge proof lets someone prove a claim without exposing the secret behind it. The prover holds private information, called the witness. The verifier checks a public statement and becomes convinced it is true. The key separation is this: trust comes from the proof, not from access to the underlying data. A classic example uses a cave with two paths connected by a secret door. The prover enters, and the verifier randomly demands, "Come out from path A," or "Come out from path B." If the prover knows the secret word, they can switch sides and always succeed. If they are guessing, they only get lucky sometimes. Repeating the challenge makes cheating extremely unlikely, without revealing the word. Every zero-knowledge proof has to satisfy three promises. Completeness means honest participants succeed. If the statement is true, the verifier accepts. Soundness protects against cheating. If the statement is false, a dishonest prover should not be able to fake convincing evidence, except with negligible probability. Zero-knowledge protects privacy. The verifier learns only that the statement is true, not the secret behind it. Together, these properties provide trust, fraud resistance, and confidentiality. This creates an important privacy shift. The verifier no longer needs to collect the underlying attributes. Instead, the wallet uses those attributes internally to prove a specific claim, such as over 18 or resident of this region. The verifier checks the proof, makes the decision, and never learns the hidden values. Interactive zero-knowledge proofs work like a live challenge-response exchange. First, the prover commits to something tied to the secret, without exposing the secret itself. Next, the verifier sends a random challenge, chosen after the commitment, so the prover cannot prepare a fake answer in advance. Finally, the prover responds in a way that only someone with the secret could consistently produce. Repeating the pattern builds confidence while preserving zero knowledge. Non-interactive proofs remove the live conversation. The prover creates a proof once, using agreed public parameters or a hash-generated challenge, and the proof becomes a portable artifact. A verifier can check it later through an API, wallet flow, QR code, or blockchain transaction. This is why many production ZKP systems are non-interactive. They fit asynchronous infrastructure, scale across many verifiers, and do not require both parties to be online at the same time. Fiat Shamir is one common way to remove the back and forth. It replaces the verifier's random challenge with one computed from a hash. The prover commits as usual, then hashes the transcript, including public inputs, to derive the challenge the verifier would have supplied. The response and transcript become a single proof artifact. This allows proofs to be generated offline and checked later, but security depends on careful hash modeling and avoiding implementation shortcuts. Zero-knowledge proofs are a family of systems, not one tool. Sigma protocols are conceptually simple and often use an interactive commit-challenge-response pattern to prove knowledge. Snarks optimize for tiny proofs and fast verification, making them popular in blockchain and compact verification workflows. Starks avoid trusted setup and scale, well for large computations, but usually produce larger proofs. The right engineering choice depends on size, speed, assumptions, and tooling. A snark is a succinct, non-interactive argument of knowledge. Its big engineering advantage is that a complex claim can produce a tiny proof, and the verifier can check it very quickly without back and forth interaction. That makes snarks useful for blockchains, rollups, mobile clients, and high volume services, where every verification step has a cost. The main caution is setup. Some systems need trusted parameters, while newer designs reduce or reshape that trust assumption. Starks and Sigma protocols highlight different design points. Starks are built for transparent, scalable proofs, especially for large computations, and often avoid a trusted setup. The trade-off is proof size, which can be larger than Snark-style systems. Sigma protocols are simpler mental models. Commit, receive a challenge, respond. They fit secret knowledge proofs inside identity and credential systems, depending on the privacy goal. In identity, minimal disclosure is where zero knowledge becomes practical. If a service only needs to know someone is over 18, it should not receive a birth date, legal name, or ID number. The holder can prove the required statement, show that the credential came from a trusted issuer, and demonstrate eligibility for a group without exposing unrelated attributes. The verifier keeps only the answer it needs, reducing privacy risk, security exposure, and regulatory burden. The core idea is simple: prove what matters, hide what doesn't. Zero-knowledge proofs provide trust through completeness, soundness, and zero-knowledge across both interactive and non-interactive models. With that foundation, we can now move into credential schemes that support practical selective disclosure.